So let's start. All right. So we'll start with the encoders for now. Yeah. So for encoders or digital encoders, they are actually devices that we use them to select one input at a time. Basically, we use them in data transmission. So let's say you have a lot of things to transmit through a channel from one point to another. Let's say in a case where you have a sender here and then you have a receiver here. You want to send some data from this point all the way to this point. So what we use these encoders for is that let's say you have a lot of things to send from here all the way to this point. What you do is instead of sending the bulk data at a go, we try to send them one at a time in a way, just to save power. So with the introduction of encoders, when one of the inputs is being allowed, or let's say it's being activated, then you see it at the output side. But then here, you would see a lot of inputs, but then few outputs because we are using binary to denote them in a way. So with the encoders, you would have, let's say, n number of inputs. And then from these inputs, you are expecting m outputs, where the relationship between the m and then the n is n being equal to 2 to the power m. Meaning here, you wouldn't get anything like anything which is not to a power of m as an input. So it means that here we can consider when m is equal to 1. When you have that, it means your number of outputs you are expecting at a time is supposed to be just 1. And then in that case, you would have n inputs as 2 to the power 1, which is going to be 2. So let's say you have this black box representing your encoder. This encoder has 2 inputs and then just 1 at the output side. So let's see if you have a 0 and then a 1 to transmit. You would need just 1 bit to represent a 0 and then a 1. So your output will just be X in that case. Mostly they represent this as, say, I0, I1. And then in that case, you would expect your output to be a 0 or a 1 at a time, because here we are saying that when we activate one input, you see it at the output side, right? But then the number of inputs that we have are a lot. So here, the simplest one you can have is a 2x1 encoder, because the inputs are 2 and then your outputs are just 1, or your output is just 1. So that's the simplest one that you can get. Now, in a case where you have outputs to be, let's say, can think of any outputs, let's say 2. N is going to be 2 to the power m still, where m is what? 2. So we have 2 to the power 2, which is what? 4. So in this case, it means you are having 4 inputs, which are corresponding to what? 2 outputs. And then we are saying these two outputs are actually binary. So we are using the binary representation for four inputs to get the outputs. And in this case, you will have something like this. So there is our encoder, which is a 4x2 encoder. Then you have your outputs like this. So let's name here, say x1 here, x0. And then your inputs, let's say I0, I1, I2, and then I3. So in this case too, when you think about it, if I activate I0, it means my output that I will be expecting will be a 0, 0. Because here you have 4 inputs. And then with 4 inputs, if you want to use 2 bits to represent them, you have 4 possibilities. The 4 possibilities will be 0, 0, 0, 1, 1, 0, and then a 1, 1. So here, at one point in time, when I make this guy a high, when I connect it to VDD, right, and I ground the rest, I ground these guys, it means only I0 has been activated, or it has been allowed to be seen at the output side. So in that case, that I0 will represent it as 0, 0, right? And then another possibility is when I ground I0, I2, and then I3, and then I activate just I1. So here, VDD is here, and then I activate like this. So here you could see that I1 has been connected to VDD. And then in digital system, it means it's a high or a 1. But then the rest are all connected to ground. So in that case, I0 is 0, I2 is 0, and then I3 is also 0. But then at that point, only I1 is a high. And then if I want to represent it in binary, let's say I'll choose 0 and then 1, like that. So let me make here x0 and then x1 in that order, since I'm using this. So in another case, I can activate. In another case, if I activate just I2, it means only I2 will be connected to VDD, which is a high. And then in that case, a 2 is represented in binary as what? A 1 and then a 0. And then in the last case, if I implement only I3 as the high, then I'll end up getting 1, 1 as the representation for what? I3 in that case. So here, that's how we use encoders. And then actually, you can think of a lot of applications of these devices. We can implement a lot with these from what you've done already, like using the combinational circuits that you've treated. So the easiest problem we can solve here is when, let's say, I want to implement, when I want to implement, let's say, an adder, but then I would like to use an encoder to implement that adder. So in an example, let's assume we have a 2 input adder. What we would like to do is, if you are asked to implement an adder using an encoder, what you need to do is to know the truth table for an adder. That's the first thing you have to know. So let's say you know that for a 2 input adder, you have, let's say, A and B. And then you have 0, 0, 0, 1, 1, 0, and then 1, 1. And then you have its sum to be 0 carry 1. Here is 1 carry 0. Here is 1 carry 0. And then you have 0 carry 1, like that. Okay. Now, when you have this, oh, sorry, here is supposed to be a 0. Sorry. So you know that here you don't need to write the simplified expression for it. You don't need it. All you need to know is which mean term is high, which mean term is 0. So here, since we are going to use SOPs, then it means we are just going after the mean terms. So you'll be looking out for the mean terms which are just high, and then use them to implement your circuits. So in this case, here, the first place is M0, here is M1, here is M2, here is what? M3. So what that means is, for the sum, only M1 or M2 gives us a high, right? And then for the carry, only M3 gives us a high. So in the implementation of a two-input adder using an encoder, what you need to do is you have to get a 4x2 encoder, right? A 4x2 encoder. And then you implement this using that encoder. That's all. I think this will work best for a decoder. So when we get there, we'll do that. Let's leave this for now. But just for you to know this, the decoder is just the reverse of the encoder. So we will note this one down. When we get there, then we implement that. So let me put an asterisk here. So to continue with this, let's try and then draw the truth table for just a 2-bit encoder. And then we'll do same for 3 bits, or let's say we just go on with 3 bits encoder. So let's say in a case where your outputs are 3, it means your inputs should be 2 to the power m, which is 3, which is 2 to the power 3, giving us what? 8. It means here you have bits running from 0, 1, 2, 3, 4, 5, 6. Let me draw another one here. 7, like that. So you would have from 0 all the way to 7, and then you can represent them with what? 3 bits. So these 3 bits, the data signals, right? We are using just 3 lines to represent each input which is activated at a time, right? So it means here you could have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, all the way to when it's 1, 1, 1, which is 7, right? So these 3 lines are what we are going to use to represent each of the inputs coming, right? So here you have 8x3 encoder, like that, right? Now, if you are asked to draw a truth table for something like this, let's say here is I0, I1, I2, I3, I4, I5, I6, and then I7. In that case, what you need to do is this. Since we have, say, I7 here, I6, I5, I4, and then we are going to use 3 bits. Let's say the 3 bits are going to be X2, X1, and then X0. So those are the 3 outputs that we are expecting at a time. It means that it means that here we are saying that only one input is activated at a time. So it means only one input is going to be a high at a point in time, and the rest will just be connected to ground. So the rest will be zeros. So you have only one input being VDD, and the rest being grounded, like that. And then here, since we have 7 inputs, let's give the first bit, or let me say the first input, all zeros to mean it's activated, right? So let's say a 0. Then the last one will be 7. So in binary, we'll represent it as what? 1, 1, 1. So when you see all zeros, it doesn't mean the signal has not been activated. No. It's just the representation for it in binary. So here, what that means is we would have the first one, which is say I0. So from this diagram that I drew, you have only I0 at a time being connected to VDD, which is 5 volts. In binary, is a 1 in that case. And then all the rest will be connected to ground like this, like that. So all the rest will be zeros for the first case. And then only I0 will be a 1, like that. All the rest, zeros. And then in that case, we are using 3 bits to represent just this input. And then we have 7 inputs. So using 3 bits, we give it all zeros to represent that. So it means that when you see 0, 0, 0 from those 3 bits at the output side, it means I0 has been activated. That's the meaning. So here the output will be 0, 0, and then another 0. And then in another case, we'll go and then activate I1. So when I1 is also activated, the rest will all be connected to ground. And then in that case, we'll give it 0, 0, 1. So whenever you see 0, 0, 1, it means I1 is the one being activated. So 0, 0, 1. Then we'll go and activate I2, some point in time I3, some point in time I4, some point in time I5, some point in time I6, and then lastly I7, where all of them, the rest of their bits will all be zeros. So here, if it's I2 that is being activated, we use 2 in binary, which is 0, 1, 0 to represent it. So here is 0, 1, and then another 0. If it's I3, then we have what? 1, 1, 1. Sorry, 0, 1, 1 in binary. If it's I4, we have 1, 0, 0. If it's I5, you have 1, 0, 1. If it's I6, you have 1, 1, 0. And then if it's I7, you have 1, 1, 1 in that case. Then now, all you need to do is to search for the inputs giving you that high, because the rest are just zeros, right? I think I have to do this well. So here is 0, 1, 1, 0. Here should be 1, 0, 1. 1, 0, 1. Okay. Then here should be 1, 0, 0. Then we have 0, 1, 1. We have this. We have that. Okay. So what I was trying to say is that if you want to get the expression for the output in terms of the inputs, let's see how that one goes. Here, you realize that if we want to write the expression for x2 is high at this point. Let me use yellow. It's high at this point, at this point, at this point, and lastly at this point. Then you go and check where you are having the one. So here is this, here is that one, here is this guy, and then lastly it is this, right? So what that means is to write the expression for x2, I4 is the only one activated, I5 is the only one activated, I6 is also the one activated, and then have I7 only the one activated. So it means we have all gates, because at some point in time you have x2 being equal to was it 6 or 5? Let's see. It's 4, 5, 6, 7. Okay. So it means you have I4 or I5 or I6 or I7 giving you x2. That's the meaning. All the rest are all zeros. So if you want to represent them in binary, it will be bar, 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 like everything bar. And then we don't really need it. If you want to write for x1, 2, you check for only the places that you have x1 as a high. So here, x1 is high here. That's I2. Another one is here. That's I3. There are two more, which are I6 and then I7. So we have 2, 3, 6, and then 7. So in that case, you have here 2, 3, 6, and then 7. Then if you want to write for x not 2, you would have here, 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 and then here. So here you have this as x5, you have x7 here too. Here you have I3, sorry. Then you have I1 like that, right? So here you would clearly see that I1, I3, I5, and then I7. So 1, 3, 5, 7. So you have 1, 3, 5, and then 7 like that. All right. So clearly you don't see any I not in any of them. It means that when you activate I not, you get all zeros, all right, but then you don't find them in these expressions because 0, 0, 0 is just 0. So it's like a ground in the output side too. So it's whether you have the input as say VDD, but in the output side, you'll be seeing it as ground, ground, and then another ground. So like 0, 0, 0. And that's the meaning. So these will be the expressions that we end up getting for the various outputs that we are having. And now if you are asked to draw, with the drawing, you don't need to stress because this one, once you have the output expression, you know what you are looking for, right? So this is just going to be OR gates between these signals. So you can draw lines like this from x7 down to x0. So x0 like this. Then with the expressions, I7 down to I0 instead. Then with the expressions that you have here, you just connect them and then you OR. So let's say I want to get the expression for x naught. What I'll need is I1, I3, I5, I7. So I have 4 things here. Let's see, this is my I1, this 3, this 5, this 7. I'll just take their inputs like this. And then if I can use 4 inputs OR gates, it means I OR them together and then my output will be X naught in that order, like this. And then you can do same for the rest of the outputs that we are having here. Now, the next thing you were taught was priority encoders. So we'll come to this, like mostly the applications are on decoders, mostly. But let's see. Now with priority encoders, what you need to know is that we give priority to one input at a time, right? So we are saying that when more than one input lines are active, encode the line with the highest priority. So in a given question, I can tell you that, let's say I have, let's say, maybe we should go with an example in the book. Let's say 8x3 encoder, okay, in your slides, 8x3 encoder. And then I want to give priority in this order. So the order of priority should be noted before you can draw the table for it. So let's say I give this question, and then from what we've done, the 8x3, I have I0 running all the way to I7. And then what I'm trying to do here is I'm giving I7 priority over I6, I6 to priority over I5, and it goes on and on and on. So in this case, so what this means is that if I7 is activated, it means from the normal encoder that we're considering, if I7 is activated, only I7 is a high and the rest are just grounded. But here, we don't do that. What we do is this. Here, you have more than one input signal being activated. So it's like you had 8 things here. I'm assuming these things. And then not only one was activated, maybe let's say these 3 were grounded like this, but the rest of them were all connected to VDD like this. So it means, let's say I7 was activated, it was 1. I6 was also 1. Let's say I5 was also 1. And then the rest were all with zeros. So it means here we still have to output just one of them at a time, although a lot are actually activated. So we give priority to certain inputs over the others. So here, what that means is we'll go back to our priority criteria that we've defined for this. And then we check if I7 is activated, I6 is also activated, and then I5 is also activated at the same time. Which of them should we give priority to? Which of them should come first? In a way, which of them should we output, right, at a time? So here, when we check the priority criteria that we've defined for it, and then choosing the range from I5 to I7, we are giving I7 more priority than I6 and then I5. So what that means is we don't really care about whether they are being activated or not. We don't care. All that we care about is the one which is having the highest priority. Then we allow it to the output side. That's the meaning. So once you are below it in terms of priority, you are just a don't care. We don't care. So here we don't even care whether you are I4 being activated, whether I3 being activated, whether I2 or I1 or I0 being activated. What that we do care about is if you don't have priority over that one, then we don't care about your value, whether you are a 0 or a 1. we still output the one with the highest priority. That's all. So here, the table that we drew for this would actually change, because let's say in the first case, you had just I not being activated. I'm just assuming. It means if I not is the only one activated at this point in time, all the rest are zeros, because we are not saying the rest are also activated, right? So the rest will all be zeros. Now, when I come and then activate I1, it means here we are saying I1 has priority over what? I0. That means at this point in time that we've activated I1, we don't care about the one below it in any case. But then all the rest will be zeros. We've not yet activated them. But let's say we've activated I1. Whether we activate I0 at the same time or not, we don't care. We still output I1 as 001. That means that whether I1 here is 1 or a 0, we don't care about it. We just activate the one with the highest priority in this case, which is going to be what? I1. So we make here a don't care. That's what we do. Then in another case where we activate I2, we check our order of priority, and then we see that the ones below it, which are I1 and then I0, have actually no power over this I2. So it means whether they are also activated at the same time or not, we don't care about their values. And then therefore, we activate what? I2 as 0, 1, 0. So in that case, I1 will be don't care, and then I0 will also be a don't care, like that. And then that trend goes on and on and on and on. So in the case where I7 is only the one activated to, you don't care about all these guys, whether they're active or not. You don't care. So they all become don't cares like that. And then you only output I7 as what? 1, 1, 1. So this is for priority encoders. And then clearly, you would see that the expressions that you end up getting for these guys would actually almost be the same as the one that you were having for the normal encoders, actually. So that one, just like what we did, the one which is active will be written, right? So maybe if we have x2, we had, let's say, I'm assuming we had x2 as I6, I4, I7, or it was only even numbers. Let me check. So I2 was 4, 5, 6, 7. Okay. So if we had this as 4, 5, 6, 7, when you go and check, you will clearly see that we have the same expression, because the rest are don't cares. When you have don't cares in your system, right? Okay, some of them are zeros, and then the rest will be don't cares anyway. When you have don't cares, you can choose not to use them, or you can choose to use them depending on what you are doing. We use them to minimize our circuits. So it depends on what you want to do. So that is that for priority encoders too. Now fast forward, let's move on to decoders, where we can have some small application questions to try our hands on. So for decoders, they are also circuits or devices that set input number and then activate only one output that corresponds to that binary input at a time. So it means here, I will flip the terms, right? Instead, I'll have M inputs, right? And N outputs. Nothing has really changed. We are just swapping them. So these are the coders. And then the mathematical expression for this will be 2 to the power m inputs, because here you have a lot of inputs that you are going to represent. Sorry, I said a lot. You have fewer inputs, right? So let me write it well. You have this. You still have m inputs like this. And then you have n outputs, which is given by 2 to the power m. So your m is your number of what inputs that you are having. So in a case where you have one input, it means you would have n being equal to 2 to the power m equals 1, which is 2 to the power 1, which is 2 outputs. In a case where you have 2 inputs, you end up getting what? 2 to the power 2, which is 4 outputs. In a case where you have, let's say, 4 inputs, you end up getting 2 to the power 4, which is what? 16 outputs. So here, when you think about it, we use both encoders and decoders for transmission of data and then the receival of data. So when you are transmitting, let's say, hi to someone, when you are sending hi on WhatsApp to someone, we convert that hi, that text, that message to binary. And then in that case, let's say H could be represented as 01001101. And then I2 can be represented as 110111011 like this. But then we have to convert this to high at the ending side again. So we will encode it using binary like that. But then here we have to even compress it. So we make use of the encoder to make it fewer inputs in a way, or let's say fewer outputs, but still inputs, because that's what will be transferred onto the channel. So let's say you have a lot of them here. You have fewer ones here. There's your channel. Your channel can be a radio channel, a fiber optic, and so forth. From this channel, let's say I had 3 coming. So I'll send 3, and then 3 will be coming at my receiving side. So here is transmission, here is receiving. From the receiving side, I'll have a decoder there. So this was an encoder, this is a decoder. Then the decoder is supposed to be giving me all those inputs that I sent. Then we'll process it. So after this, it goes through some processing. And then from that processing, we'll end up getting, let's say, the high that I was sending at the input side. So here, your high will go through also a process to enter the binary stage. You will learn about this when you get to 3rd year. So the decoding part of our circuit is just to give us back what we were trying to send. So when you are speaking with someone, you speak, then the person hears what you are saying. It's because we have some of these devices working for us. So with this decoder, we would actually do something similar, just like the truth table here would change a bit, but it's not really anything different from what we've been having, right? It's not really a different thing. So when you check, let me zoom in this part of your slides for you. When you check, I'm coming. Okay. So when you check this 3 to 8 decoder, what you see here is you have inputs which are 3 bits, right? A bit 3 by 8 decoder. So here we are telling you that the 3 bits are actually binary. So it means if you have 3 bits, you would have 8 possibilities, where the 8 possibilities can run from M0, which is 000, all the way to M7, which is 111. And then in that case, we are going to output just one, right, at a time. So it means if you have 000, only O naught, right, will be high or will be activated. If you have 001, only O1 will be activated. If you have 010, only O2 will be also activated, and then it goes on and on and on in that order. So here, if you want to write the expressions for it, O naught will just be like writing a 3-input, let me say a 3-input expression for 0 in a way in binary. So that one, it means you have A bar, B bar, C bar, because they are all zeros here, here, giving you O naught. So this will be O naught. Now, if you want O1 will be when A is high or 1. So that one, it leaves us with A. When B is 0, it will become B bar in meantime. And then C also becomes B bar because it's 0. And then you run from that all the way down. So here, if you are supposed to draw for this, you just draw your lines. And then since you know that you have some bar inside, you have to represent the logic and then its inverted form so that you can utilize both of them in finding the expressions for the output side. So clearly, when you look at this decoder hat, you realize that here is actually M0, here is M1, M2, it goes down to what? M7. So now let's take one example and then solve. Now, just like what I started with, let's implement the half-adder using a decoder. And then in this case, you know that this half-adder has 2 inputs, right? So you would have, let me say, 2 bits. So here, if you need a decoder for it, the decoder should be having a 2x4 decoder, right? So here, what that means is we would have, let's say, a black box. We'll have 2 inputs, let's say A and then B, like this. And then we expect to get 4 outputs from this A and B. So A and B can give us, so this is a 2x4 decoder. From A and B, we expect 4 different signals. Now, these 4 signals, one of them is 0, 0. The next one is 0, 1. The next one is 1, 0. And then the last one is what? 1, 1 in that order. So this corresponds to M0. This is M1. This is M2. And this M3 in that order. Then after knowing this, the next thing you are supposed to do is you ask yourself, how does the truth table of a 2-input half-adder looks like? So you have A here, you have B here, you have sum, and then you have carry. You know that the output of these 2 bits, A and B, which are here, gives us 4 outputs. But then the 4 outputs, which of them give me a sum? And then which of them will give me a carry? So you draw the truth table like this. And then from this, you'll be able to tell which of them will be your sum and then which of them will be your carry. So here you have 0, 1, 1, 0, and then you have 0, 0, 0, and then 1. So clearly, you will notice that only M1 and then M2 gave us a high for sum, right? So what that means is, if I want to implement the sum, I'll have M1 or M2. In that case, if you want to represent that in binary, we wrote sum to be A bar B, right? Which is this part, and then this part as what? A, B bar. So clearly, the main terms that were giving you that A bar B was M1. And then the main term that gave you this was also what? M2. So for you to design a half adder with this decoder, your sum will be M1, which is this signal, and then M2, which is this signal. Then we are supposed to what? All them together. So we will all them like this together. And then the output will be our sum. Like that's so simple. Then also, if you want to get the carry only this part was 1. So carry was A, B. A here, B here, which is actually M3. So what that means is my carry is just when I connect M3 like that. If I want to design my carry, this will be it. Then the ones which are not being in use or which are not utilized, you can actually ground them. So I can actually ground this guy like that. It will not form part of my half adder. So this is a half adder implementation using what? A decoder. That is it. Any question up to this point? Like I've not asked you guys about that. Any question for me up to this point? No question? Okay. Let's move on. So let's then do this. Let's now implement a 4 adder using a decoder. So here too, you should know the main terms which are going to give you a high for the sum and then for the carry. So you need to know the truth table for the 3-bit words 4 adder. So let's say I have this, have that. Okay. Now here is my A, B, C. And then I'll have sum and then carry. So sum here and then carry here. So here 1, 2, 3, 4, 5, 6, 7. Let me draw the last one here. 8. Like this. Okay. So from this, let's fill the table. We have 0, 1, 0, 1, 0, 1, 0, 1 ish. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So this wasn't needed. We have 0, 0, 1, 1, 0, 0, 1, 1. We have 1, 2, 3, 4. 1, 2, 3, 4. Okay, like this. So here, let's view the table. It means in your answer, you wouldn't draw the truth table. It's not needed. So right from today, if you should chew this into memory, do that, like just commit it into memory. So here your sum will be 0, your carry will be 0. Here your sum will be 1, carry is 0. Here your sum is still 1, carry is still 0. Here sum is 0, carry is 1. Here is 1, 0. Here is 0, 1. Here another 0, 1. Here is 1, 1, like that. Okay, so here clearly we can write the signals giving us high, right? So here for sum, I will do sum here, sum on the left and carry on the right. So for sum, I have M1, I have M2, main term 1, main term 2. here is min term 4 because it's 100. And the last part is min term 7, M7. So this will be my sum, right? And then carry will also be this, this, and this. So this one is when you have 0, 1, 1. 0, 1, 1 is M3. This part is when you have 1, 0, 1. 1, 0, 1 is 5. So M5. This one is 6. This one is 7. So this is my carry. So right from this truth table, you realize that your sum is given as M1 or M2 or M4 or M7. And then your carry is also M3, M5, M6, and then M7 in that order. So from this, your decoder will be looking like this. You have 3 inputs, which are, let's say, C, B, A, or A, B, C. I'm reading it in the upward direction. And then your outputs are going to be 8. So 1, 2, 3, 4, 5, 6, 7, 8, like that. So here is M0, M1, M2, M3, M4, M5, M6, and then M7. So 3 by 8 decoder, like that. Now, from these outputs, you ask yourself, which of them are giving me the sum? So sum is M1, so you go and tap M1. M2, you go and tap M2. Let me do this. You have M4. So M4, I'll come and tap like this. And then you have M7, M7 too. I'll come and tap. Then I have all these bits or main terms together like this. And then this will be my sum. Then the carry is supposed to be M3, 5, 6, and 7. So all of them are down here. So I'll take this, take it here. This thing is okay. So it means M3 is here. I'll take this one here. I'll take this here. I'll take this here. And then here, this one, I can take it like this. So all these main terms, I have to add them together to get what? My carry. So this is how you get your sum and then carry for a full adder. Now with these two, M0 is not seen, right? M0 is not part. So here you ground it because you don't need it. You just ground because you don't need it in the output side. So this will be your sum and then your carry for a full adder. So this is a full adder using what? A decoder in that case. So these are some of the examples that you should be expecting in your end of term. These are some of them. It could also be that he can give you a truth table for, let's say, a multiplier. And then from that truth table, you just need to know the main terms which are giving you a height. For, let's say, let me have just one example here. You can take your comparator example. Your comparator, right? Let's say a 2-bit. Let's use a 3-bit comparator, for example. So let's say here you have, I'm using a 3-bit. That's wow. Let's say you have A and then you have B, but A is represented with 2 bits. So A1, A0. And then B is also 2 bits, B1, B0. And then you are told to compare them. Let's say when the conditions that he can give you is when A is greater than B, your output should be 1 or a high. When A is less than B, your output should be a 0. And then when A is equal to B, your output should also be a 1. So in that case, you draw your truth table, right? Or he can actually provide you with a truth table, because something like this, you wouldn't have it in mind, right? You wouldn't have it in mind. So what that means is, let's say I'll draw my truth table A1, A0, like this. Here is going to be like a whole lot. It's going to be like 4 bits. So 16 truth table, 16 input truth table. So B1 and then B0. And then you have, let's say, your output as Y like this. So you could have 0, 0, 0, 0, 1, 0, 1, 0, 1, all the way to 15 and 15. And here too, you read. Then you'll be checking. If here is 0, 0, you compare it with, let's say, 0, 0 like this. They are equal. So the output should be a 1. Because here, the 2 bits will give you 0. Here to the 2 bits is giving me 0. So 0 equals 0, A and then B. So the output should be 1. Then you write 1 here. In another case, let's say, I think maybe I have to complete this table so that we'll look at this very well. So let me draw it well. Let's do this. So here, this is the question. The question is, you have a 2-bit comparator, right? 2 bits. Now, the 2 bits, you have A and then B representing them. In the case where you have A greater than B, your output is a high. When you have A less than B, your output is 0. And then when you have A equals B2, your output should be a high. So here you'll be comparing A1, A0 to B1, B0. You convert this to decimal, this also to decimal, and then you compare them. So if you have 0, 0 comparing with 0, 1, it means here is 0, here is 1. And then 1 is greater than 0, means your output should be a 0 in that case. So that's what we are going to use or implement. So let's do it. I think you have A1, A0, have B1, and then B0 like this. So I'll draw my lines. Then you have your outputs. Let me use red for this. So this 1, 2, 3, 4, 5, and 6. Let me draw some in between 7, 8, 9, 10, 11, 12, 13, gosh, I'm coming. Okay, 14, and then 15. Interesting. I would like to clean one of them, but let's go. So let's fill them. Here you have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's left with one table. Supposed to be 16. So another one like this. Then I would have a 1 here. Nice one. Then 0, 0, 1 1 0 0 1 1 0 0 1 1 0 0 and then 1 1. Have 1 2 3 4. Then I'll flip. Have 1 2 3 4. I'll flip it. Here I'll have 2 to the power 3 zeros. So 4 here, another 4. Ish. 4, another 4. Okay. Have the rest all being ones. So here, with this comparator, clearly, you would realize that the first part is 0, 0, comparing with another 0, 0. So it means 0 equals 0. So the output should be a high, right? That's what we're trying to say. The output should be high. So I'll have 1 here. Now I have 0, 0 as A, which is 0 in decimal. And I have 0, 1 as B. That's 0 comparing with 1. Since 0 is less than 1, the output should be a 0. Then here too, I have 0, 0 comparing with 1, 0, which is 2. So 0 is less than 2. So the output is 0. Here I have 0, 0 comparing with 3, which is 1, 1 here. So the output is also a 0. I have 0, 1 comparing with 0 here. The output should be 1. I have 0, 1 comparing with another 0, 1. So the output should be a high. Here I have 1 comparing with 2. So the output should be 0. We have 1 comparing with 3, so 0. We have 2 comparing with 0. 1, 0 is 2. 0, 0 is 0. So here is 1. Here, 2 comparing with 1, so high. We have 2 comparing with 2, so another high. 2 comparing with 3, so 0. Okay. Now I have 3 comparing with 0, 1, 2, and 3. So all the outputs should be high. Like that. I don't need to check them one after the other. So here too, clearly, you would see that this is M0, right? Here is 0, 1, 0, which is M8. Sorry. Oh, 0, 1, 0. Let's say M8. So 0, 1, 0 in binary is what? 2. Or M2. Am I looking at this for? Oh, that's fine. It's 0, 1, 0, 0. So it's 4, M4. Sorry. And then you have here 2 as 5, M5. This place is 8. This is 9. This is 10. And here you have 1, 1, 0, 0. 1, 1, 0, 0 is actually 12. So here is 12. Here is 13, here is 14, here is 15. When they give you binary, what you need to do is this. You know that 4 is 1, 0, 0. So if I give you 1, 1, 0, 0, it's 8, which is 1, 0, 0, 0 plus 1, 0, 0. So here is M8 plus M4. So this gives me 12. So in a case where I have let's say 1, 1, 1, 0, 0, 0. And I tell you to solve for this. We just need to know where you are going. In a way, here is 1, 2, 3, 4, 5, 6. You ask yourself, what is 2 to the power 6? That's when you have all of them being, let's say, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. Being ones like that. Then you come and subtract from it one after the other. So that's how we do it. And so this one, from this, we know that this 2 bits comparator, if we want to implement this using a decoder, it means the output Y is supposed to be what? M0 or M4 or M5 or M8 or M9 or M12, sorry, M10 should come, okay, or 12, 13, 14, and then 15 like this, right? So we expected these outputs. So once you know that these are the outputs that you expect, then your drawing becomes much simpler for you, because here you just need to draw your black box, which is a 4-bit by 16 output. So 4 inputs, which are A0, A1, and then B0, B1. Let me do it here. A0, A1, and then B0, B1, like this. So 4 is to 16, you have 16 outputs. So M0, M1, M2, all the way to M15. Then you just connect. So you check the outputs here. Which of them are giving you a high? Then you just all of them together, and then you place Y there. So let's say I'll be having to this, and then this will be my Y. You just connect them. So M0 was parts. Another one will be parts. Another one was parts. So like that. Then you get your outputs. All the rest, which are not parts, let's check here. I don't see M1 as part of them. I'll ground it. M2 is not part. I'll connect here like a short. Both of them are grounded. M3, I'm not seeing it there, so I'll join them. That one to grounded. M4 is part, so let's say this one goes to M4. M5, when I check here, is part. So let's say the next one will be M5 going like that. So in that order, you just draw and then you connect. And then from this expression, they are just all together. Then you just add the outputs, just like that. So something like that would be your 2-bit comparator using a decoder. Let me draw it well. I think I have to. So let's see. Okay, so I have M nodes here. M1, M2, M3, M4, 5, 6, 7, 8, 9, 10. Okay, let me do 11 here. This too long. So let's say 12, 13, 14, and 15 like this. So I have this. Okay, so I have it like this. Then now you just go and check your expressions for the output Y. So Y was giving us, what? 0, 4, 5, 8, 9, 10, and then 12 to 15. So 0, 4, 5, 8, 9, 10. So we are just going to look for 0, which is this guy. So I'll tap here. So let's see. Let me reduce this a bit. So 0 will be here. 4 is somewhere here. 5 is somewhere here. Then 8, 9, 10. So I'll bring them here. 10 is here. Then the rest are 12 all the way to 15. So 13, 14, and then 15 like this. Then what do I need to do? I have to all these outputs together. And then they will give me Y, which was my output for this 2-bit comparator in that case. And then since the rest of the outputs that you are having, you don't need them. What you need to do is to put them to ground. So here, the rest of the outputs are from this. So I'll connect this to M9. Sorry. made a mistake. M9 is fat. I'll connect these two, M7, connect it to M6, connect it to M3, connect to M2, and then M1 respectively. Then I'll connect all of them to ground like this. Then I'm done with this question. So this is how questions will be asked when you are told to do something on decoders. Yes, so this actually the 4 to 16 decoder that we use to implement a 2-bit comparator, which is A1, A0 between this and then this guy. Okay. So it depends on how the question will be framed, because he can actually give you any case state. Could be that he will tell you that if B is rather less than A, you output a high. And then it means in that case, your circuit will actually change a bit. It will look a bit different from what we are ending up with here. Right. So that's that. Any questions from the start up until this point? Any question? We've done this also. Any question before we move on to enables and then decoder tree? Any questions? Okay, no one has a question. So let's move on. Now, another thing we are supposed to note here is something we call enable. So enables or enable, as the name suggests, is just a signal, right? It's just a signal, an input signal, which is to, if I should use the word enable again, but not, I wouldn't use the enable again in this case. So enables are just to allow certain inputs, right, to the outputs. So they are to allow, or the term enable, as the name suggests. So when you want to send a signal from your inputs to the outputs like this, so this is your inputs, this is your outputs. If let's say I connect an enable here, sorry, this the enable. If this is my enable, then if this enable is not high, whichever input that you are having here will not be seen at the output side, wouldn't it? So what that means is here you could have, let's say, this case, let's say you have a data input, right? Your data input, let me use a buffer for this. Let me use a buffer for this illustration. So in a case where, let's say, I have this, and I have this is my inputs, and this is my outputs. And then I have an enable here, right? And then to let you know, enables can be either 1 or 0, depending on how they are implemented. But whichever way, if it's a 0, you should know how to represent them. If it's a 1, you should know how to implement them. So let's say if I implement something like this, and then I put a note here. This note here should tell you that it should be a 0 for me to be able to make it a high in the system in a way. So here it wouldn't be a 1 that you need to enable it. So here I'm trying to say that here your enable will be bad. So if it's 0 coming, it's 0 bar giving you a high to enable it. That was what I was trying to say, actually. So in this case, we are having we call it active high enable in this case. And then in a case where you would have something like this, we call it active low enable. So note these two. So here we represent it as E bar because it's only when your input is or your E is 0, your enable is 0, that you would be able to activate this system here or this buffer for you to transmit your input to the output side. So we call it active low enable in this case, this representation. And then the first one is active high. So here E has to be 1 before you'll be able to activate the system, or you'll be able to send whatever is at the input side to the output side. So with these two guys, we would have two different truth table for them, because this needs a 0 to be activated, but then this needs a 1 to be activated. So what that means is, if let's say I'm going with active high enable, which is this one, the first one, so 1 and then 2. If I'm going with 1, what that means is, if E is not high or 1, whatever input that you have here will not be seen here. No, it wouldn't. And then for 2, if the enable is not a 0, whatever input is here will not be seen at the output here. It wouldn't. There's just a buffer that I'm using to explain this. So let's use this case for an enable. Let's say I have A and B, 2 bits data that I want to transmit. And then I'm supposed to get some output. So let me name the outputs. Let's say Y. And here is my enable. Here I'm using active high enable. So when it's active high, you should know that it's only when the enable is 1 that your inputs will be seen as your outputs. If it's a 0, your inputs will see a high impedance. In a way, it will see a high impedance. So it wouldn't be seen at the output side. Yes, that's what it means. So here, if let's say I have 0, 0, 0, 1, 1, 0, 1, 1, like this. Oh, sorry. So I have this, something like this. I'm assuming we have this table. If we have this, what that means is, if I place 0 here, 1 here, 1 here, 1 here, what that will mean is, when this guy is 0, right? When this guy is 0, whichever input that you are having here will not be seen at this output. So here it will be a dash. Let's use a dash for it. It's not like it's going to be a donkey. It will be seen as an impedance in a way. So I can even use Z as impedance, because we represent Z as impedance in engineering, like electrical engineering. Z is impedance. So it's seen as an open circuit. So it's like you have your buffer here like this. You have your buffer here. Your buffer here has some circuit like this. Let's say this is your enable. So this is your enable like this. And then there is Z here. This is your output. When your Z is not high, right? Let me draw the buffer like this instead. Let me have this rather. So it's like a switch. So this is Z here. Now, if E is 0, whatever that is here, let's say you are transmitting a high 1 will not be seen at the output. No, you wouldn't see 1, but rather you see a high impedance, which is an open circuit like this in your system. So it's like 1 is here, you want to transmit, but the circuit will not close. You need an enable to be 1 for the circuit to close before you see it at the output here. So in this case, it will be seen as this. Please give me some few seconds coming. And okay, I'm back. Let's continue. Okay, so it means that if your enable E is 0, then yes, your circuit will be seen as an open circuit like this. So you will see high impedance at your output side. That's what it means. But if your enable is 1, and then let's say you are transmitting a 0, you have 0 here, but enable is 1. It means you close this switch and then the 0 will fall down to your output like this. And then in a case where your input is 1 like this, and then your enable is also a 1, that means it will close the switch for your input to flow down to your output as a high like this. So that's the essence of using enable in our systems. So sometimes you don't want signals to be seen as your output side. So when they come, you have to, in a way, open your circuits. Right? You have to open your circuits. A simple example you can give is as electrical engineering students. In power system protection, we use, let's say, relays, right, to protect certain, let me say, devices or components that we use, right, or elements, together with, let's say, circuit breakers. So let's say, some point in time, if you have overheating, right, let's say you are using a motor, this is your motor, and then you have overheating. You have this guy as your circuit breaker in a way. So if it sees something which is too much for it, your enable will no more be a high for this circuit to close. It will now be a 0, so that it will open for you to see high impedance. So this motor will not get the signal at all. Let's say 1 is supposed to run the motor. When E, which is your over current or something, is coming, enable will now see it. That's your, let's say, your relay. Your relay will be used as the enable. So it will break the circuit for you so that you see a high impedance here, so that you can protect this motor. Okay, so that's the implementation of enables in circuits. And then I'm saying that you could have an active high enable and then an active low enable. So let's say in this case, if you have 1 here, right, and then you are sending 0, 1. Let's say you see, I'm just using main terms here. So let's say you see A bar 3 here, like that, or main term 1. I'm just using this as an example. And let's see, here is 1, here is 1, 0. Then you see what? A, B bar like that at the output side. here is 1, enable is 1 or high, and then you are sending 3, which is 1, 1. Then you see AB at the output side, right? So it means here, if you want to draw a circle for it, you have, let's say, A here, you have B here. Your enable 2 is also here. And then let's say your enable bar is also here, like, so this E bar. E bar, you see high impedance, so we don't really need it because it's not supposed to be part of the output side. So each of the outputs that you'll be considering here will be having the enable attached to it in a way. This is just an example. This is not a practical question that you can get. So let's say the first case you had A bar. So let me note here. Let me have another note here. Let me do this. So you have this connection here like that. And then B bar also. So you have this connection here. This will be your first expression. But then your enable was also high, so you have to put the enable there. So it's like enable A bar B, like that. Then if you want to get AB, let's say this one, the enable is also high, like that. Your B is also high. So you add all of them together to get AB, but the enable 2 was cut. So there is just an example of it. In a case where you have, let's say, active low enable, it means that if I'm considering this table and then this, let's say this your Y, this your enable, it means if here is 0, whatever that is here will be seen here. If here is 1, whatever that is here will not be seen here. So what that means is here I'll represent it as E bar because it's active low enable. Okay. So what that means is, let's say I have 1 here, 0, 0, 0, 1, 1, 0, 1, 1. Now I have 0, 0, 0 here, like that. Right. So what that means is if this is 1, right? If this is 1, whatever that is here will be seen as impedance. But if this is a 0, then it will activate the system for me to see M1. If it's this, then I'll see M2 here, I'll see M3 here, like that. So in that case, you'll be making use of if you have E here, you'll be making use of the E bar like that, together with, let's say, your A and then your B, like this. So if I want to implement, let's say, M1, I'll have A bar. So I'll have this. I'll have A bar and then B, like that. So A bar, I'm making connections here and then here. So A bar B will give me the output when I have E bar in that case. So this E bar, A bar B. Right. If I have E, I will not see the input at my output side. That's the use of enables in the system. And then here too, we have something we call decoder tree, where you can use smaller number of encoders, like smaller encoders to implement larger encoders. So we'll look at that too. So this common combinational circuits, you have an IC here, which is 74AOS138, 1 to 8 encoder, like that. 1 of 8 encoder, sorry. So here is a 3 by 8. I'm saying encoder, decoder, a 3 by 8 decoder, which has some enable mechanism. And then the enable mechanism too, you have them as 3 bits. They have represented them as 3 bits. You have some of them being active high and then 2 being active low. So check. See this, an active low, another active low. This active high. So you see them being bad like this. If it's active low, it means you need a 0 to activate it. And then if it's active high, you need 1 to activate it in that case. So here, all that you need is this. If you want to activate the system for your input combinations here to be seen at the output side here, you have to make E1 0. So 0 bar is what? 1, like that. E2, you have to make it 0. So E2 should be a 0. So that when you bar the 0, you get what? A 1. And then E3 should stay as 1. So that you have E1 bar, E2 bar, and E3 being 0 bar, 0 bar, and then 1, like this, giving you 1 times 1 times 1, which is what? A high in a way. Let me see, a high. To activate your system for you. So in this case, if you have them as 0, 0, 1, you have 0 bar, 0 bar, and 1 multiplying together or added together. So that your input combinations, which come around from 0, 0, 0 all the way to 1, 1, 1, will be seen at the output side here. That's the whole meaning of this. Yes. So when you check these combinations, the expressions that you end up getting for them is what you are seeing there. Actually, there is not any difficult thing. Right? So let's continue. Now, let's say I would want to implement, let's use this example to look at the decoder tree. So if I want to implement a 3x8 decoder using a 2x4 decoder, what I'll do is I would actually have something like, I want to implement this 1, 2, 3, 4, 5, 6, 7, 8. I want to implement this 3x8 using a 2x4 like this. And then I have another one like this. I want to implement this with this with these two guys. Now, clearly from here, you would realize that I have 4 inputs here. And that's a problem because I want to use 3 inputs to implement 8. The 8 is what I'm having here. So that one is normal. But then there's a problem here. The inputs are 4. So what comes in mind is I have to use 2 of the bits. I have to connect them together and then implement them as an enable. But then I have to also take notice of something. Both this guy and this guy cannot be on at the same time, right? They can't. Because if they are on at the same time, then it means you are implementing, or let's say you are outputting 2 things at a time. Because if you activate this guy and then you activate this guy, one output will be here, one output will be here, which goes against the rules of a decoder because we activate one output at a time, right? We activate one output at a time. So what we need to do is we have to implement the enable in such a way that when an input is being activated or enabled, just one of these 2 decoders, just one of these 2 will be activated, and then in that case, we'll have just one output at a time. So this is how we go about it. So we want to do 3x8 using 2x4. So what I'll do is this. I'll draw my 12x4, both of them down like this. So this is the first guy. This is the second guy like this. So I have my 4 outputs here. Have another 4 outputs here. So my 2 inputs here my two inputs here like this. Now I'm supposed to get just 3 inputs and then 8 outputs. So my outputs, I can name them I0, I1, I2, I3. Here I continue with I4, 5, 6, and then 7 in this case. So this is 2 by 4. This is another 2 by 4. Do this. Now what I'll do is I'll make this guy I0. Sorry. I've made here inputs. Let me do it output. So O or O. So I'll make here I0. Then I'll make one of them I1 and one of them I2. So that I'll get the 3 inputs, right? But then thinking about it, only one output should be seen at a time. So I can't activate this and this at the same time. So I have to use an enable where that enable, one should be negated or active low and one should be active high. So what I'll do is I would, since this runs from 0 all the way to 4, it means the activator for this should be an active low. So what I'm trying to do here is I'm implementing the enable as the MSB, the most significant bit in that case. So what I'll do is I'll say this is also I1. Then this guy, the last bit here, these two guys, this and then this. So this the one going here. There's the one to going here. Then these last two, I will implement it as the enable. But then it should be the one going to be seen as my what? My how do you call it? My MS. But then we still have a problem here in a way because we need 2 inputs here. So what we'll do is this. We will actually take the 2 inputs as normal I0, I1, because we still have to get 2. If we do that, we'll have 1 to 4, which is not 2. We should have 2. So we'll implement it as this. Here, we'll take this one as also I1. And then we'll give here the same inputs. We'll give here to the same inputs. So same I0, same I1, where I0 and I1 can run from 0, 0 all the way to 1, 1, like that, right? Normal. Then we would actually implement the enable somewhere here as the third input. So the enable is actually, you see, when I was implementing the buffer, this will be my enable. The enable is not part of what will be seen at the output side, right? It's not part of the input that will be seen at the output side. No, it's just going to enable it. But here, we are going to use the enable to implement this in a way that the enable will be seen as one of the inputs, right? So it will be seen as the third input that will be given to these decoders, these 2 by 4 decoders. Where in that case, we realize that the first decoder runs from 0 all the way to 3. Sorry, here should be 3. And here from 4 to 7. And from 0 to 3, all of them, if I do 3 bits, have 0, 0, 0 all the way to 0, 1, 1. So all of them, they are what? Their MSB is what? Is a 0. Then for this second decoder to when you check, it runs from 4 to 7. And from 4 to 7 is 1, 0, 0 all the way to 1, 1, 1. When you check, their MSB is also what? MSB is also what? High, 1 like this. And then both of them have inputs 0, 0 to 1, 1, 0, 0, 1, 1 like this. So I can use I0 and I1 as both inputs to the 2 decoders that I'm having here. Then my MSB is what I need now. So I need an MSB here and then here. That MSB, I'm supposed to implement 0 for this guy and 1 for this guy. And that's what we are going to use as the enable signal. So if this is supposed to be the case, then why not put a NOT gate here and then use it as the enable for this guy? And then put a high here. So I'll tap from this line. I'll tap from this enable line from here, and I'll give it here as the enable signal for the second one. So that here my 3 inputs will be E, I1, and then I0, where I1 and I0 can run from 0, 0 all the way to 1, 1. So I have 0, 0, 0, 1, 1, 0, and then 1, 1 as I0 and I1. And then I could have 2 possibilities where if E is supposed to be 0, 0 will be seen here. It will flip it right, and then it becomes 1 here to activate the system. So you have E0 bar, I1, I0 for the first decoder. And then in that case, whichever inputs I1, I0 will be seen as what? The outputs. So in this case, when I implement this E as a 0, it becomes a 1 here. At that same time, I use this signal, the high signal, as the enable. So here I'll name it enable here. Here to enable here. I'm using this same E as the enable signal for this second decoder, which means when this enable 0, the 0 will be shorted all the way here, which is 0. It means here it should be what? Active high enable. That means that this being 0 means you will see a high impedance here. So whatever that is at the input here and then here will not be seen at the output side. So in the first case, this will be disconnected. It wouldn't show. So here, when you have 0, 0, you will see I0 at the output. If you have 0, 1, you see I1 at the output. If you have 1, 0, you see O2 at the output. And then you have 1, 1, you see what? O3 at the output in that case. And then in the case where I have the enable as high or 1, if E is 1 here, so the first decoder will be implementing E bar I1, I0, because here has been flipped. There is a NOT gate here, right? That's the mean. So when, in a way, let me use E bar, because 0 will be flipped to become a 1. So you have 0, 0, 0 bar, 0, 1. You have 0 bar, 1, 0. You have 0 bar, 1, 1. This will represent O0. This will represent O1. This will represent O2. This will represent O3 in that case. And then for the second one, when my enable now, E changes to 1. As soon as E changes to 1, E is 1 here now. Now when E is 1, 1 will flip here and then becomes a 0 here. So it will disconnect this first decoder. This one will be disconnected in this case. And the 1 will be shorted down here. So this 0 that I wrote here now becomes what? A 1. Now the enable high has been activated. So whichever inputs that you are having here will be seen at the output. So in that case, you have E, I1, I0 like this. So if it's 1, here 1, 1, you have 4 possibilities. 1, 1, 1, 1. So you have 0, 0, 0, 1, 1, 0, and then 1, 1. And then this looking like 4. This looking like M5. This looking like M6. This looking like what? M7. So this 06, 04, all the way to 07 in that case. So here, it means we've been able to use a 2x4 decoder to implement a 3x8 decoder, where we made use of what? An enable. Right, the enable. And then we implemented that enable as the MSB, the most significant bit. So that's the most important thing you are supposed to note here. So the most significant bit you are going to use is your enable signal. But your actual or your true inputs are actually I0 and then I1 respectively. Right. So I hope this is clear. If he wants to give you a question on this, he can ask you to implement, let's say, 4/16 using, let's say, 2/4. You can have that, which is also normal because you have 2 here, you have, say, 2 here, another 2 here. So here, how you do the calculation is this. You have 16, right? You want to get 4 outputs here. So you divide by 4 first. Then you get 4. Then you circle this guy. Then you come and do 4 divided by 4. Sorry. Let me do this. Okay, actually, I can be using that. So 16 divided by 4 is 4. I circle, I come and divide 4 by 4, I get 1. So I'll need 4 plus 1 of them, of the 2/4, to implement this. So if I want to implement 4/16 using the 2/4, it means I'll need 5 of the 2/4 decoders to implement it. This is how we do the calculation. Anyway, this is how we do the calculation. So I think he taught that also in class. Then now you think of how to connect them. So how to connect them? You'll be using, at some point in time, you'll be using some of them as what enable signals from one point to another, enable signal. So your actual true inputs are just 2 in this case. So I'm doing this. Your actual true inputs are going to be, let's say, I0 and then I1. All the rest will be enabled. So this will be given to the first 4. These same inputs will be given to the next 4. These same inputs will be given to the next 4. The same inputs to the next 4, like that. But then now how to connect these guys, the rest will be enable signal. That's how we implement it in a way. So you think of how to get the enable for this. But then we are saying that we are going to need 5 of them. So where is the last one? Maybe I can put the last one here. Right. So if I put the last one somewhere here, right? Let's do this. Let's do this. So I will put the last one here because we said 4/16 using what 2/4. What we'll do is we'll compare this with 4. So we'll do 16/4, which is 4. And then we'll come and take this 4. So you circle it. Then you divide by another 4, you get 1. Then you come and add those that you've added. Sorry, circled. So you get 4 plus 1, which is what 5. So it means here you are going to implement 5 of the 2/4 decoders to implement what a 4/16 decoder. So what that means is this is the first one, this is the second one, this is the third one, and then there's the fourth one. So here it runs from O0 all the way to O15 like this. Let me clean this part. Okay, let me leave it there. Now, this last 2/4 encoder, right? These 2/4. This will be our, say, I2. This will be our I3. So this will be the 4 bits, right? Giving us these 16 inputs at the output side. Now you will ask yourself, where are the rest of the 4 bits going to? Where would they go to? That's the question you have to ask yourself. Now, that question will be solved by this. We will go and implement these 4 outputs as enable signals for each of the 2/4 decoders that we have here. So we'll connect this first one to this guy. Then we'll connect this second one to this guy as enable. we'll connect the next one to this guy to as enable. And we'll connect the last one to this guy also as enable. So all the green lines you are seeing there are enable signals, right? They are enable signals. So what that means is this enable, when the output is 0, 0, the enable signal will choose this guy. Let's say this is E0. Let me make here E0, here as E1, here as E2. Let me use a different color. This color is looking some way. So let me use black. Let me go with black. Okay. So here, let's say here is E0, here is E1, here is E2, here is E3. It means when I2 and then I3, you have them as 0, 0, you enable this guy. So you enable this guy when it's 0, 0. This one is enabled. Then all these ones will be disabled at that point in time. When I2 and I3 are 0, 1 respectively, we'll see why here should be 3, here should be 2. Because I'll be using this guy as the MSB in this case. So if you have 0, 1, E1 will be enabled. And then in that case, here is 3, here is 2. So in that case, if you have 0, 0, I'm sorry, my network disconnected. Let's continue. Okay, let's continue. Let me share my screen. Right. All right, nice one. So let's continue from where we left off. Okay. Okay. So this was what we were considering. Now, in a case where 0, 1 is also activated as I3 and then I2 respectively, it means that E1 is the one going to be what's activated. That means, let me name here decoder 2. Here is decoder 1. Here is decoder 3. Here is decoder 4. So it means when I implement I2 and then I3 as 0, 1, it will go and select this second decoder. When it's 1, 0, it will select E2. Then E2 will enable the third decoder. When it's 1, 1, E3 will be enabled. And then E3 will enable the last decoder. Let me draw that. That's 9. So this two, this one too, like that. So this is how you implement a 4x16 decoder using a 2x4, right? A 2x4 decoder. So it means the last one that we calculated for, we said we are going to use 4. The 4 will give us all the 16 outputs. All right. Then the last one will be our select signal or the enable, right? So if we have this, then it means this first decoder runs from O0 all the way to O3, like output 0 to output 3, representing the first 4 that we can get. So let me clean this part and show you something. Let me clean this and show you something here. All right. So it means that we would have something like this. This first decoder runs from O0 all the way to O3. This O4 to O7. This from 8 all the way to 11. And then there's 12, 13, 14, 15, right? Like this. So when E0 is activated, which is I3 bar, I2 bar, or 0, 0 for these two signals, then that one will be activated. The first one, the first decoder will be activated. So this gives us O0 all the way to O3. In a case where E1 is activated, which is I3 bar, like 0, 1, so I2, it means O4 will be the one enabled, and then all the rest will be disabled. Because at that point in time, E0, E2, E3 are all not shown at the output side. So the enable is 0 in a way. That's the meaning. The enable for all of them is 0. So they are all deactivated. Only decoder 2 will be working. So that one will move from 04 to, sorry, 04 to 07, like that. And then when E2 is also activated, which is E3, sorry, I3, I2 bar, which is 10, it means O8 all the way towards O11 will be activated. And when E3 is also activated, which is I3, I1, it means that O12 all the way to O15 will be activated. Now, one question you ask me is, why did I swap I3 and then I2? Because in the first case, I did I2, I3. What I was trying to do was this. You need 0, 0, 0, 0, all the way to 0, 0, 1, 1 for the first decoder, which is O0 to what? O3. This is decoder 1. Now, let's continue. You need 0, 1, right? 0, 0. So look at the last 2 bits. They all runs from 0, 0 to 1, 1. For the second decoder 2, you need 4 to 7. 7 is 1, 1, 1, right? So here too, you need 0, 1, 0, 1 again. And then here 0, 0, 1, 1 for the two inputs, I0, I1, respectively, or I1, I0, whichever way. Now, this is 04 to 07. This is decoder 2. Now, for the third decoder, you need 1, 0, which is 8, because there is 7. 8 is 1, 0, 0. So this 08, 011 will be what? 1, 0 again. But here it will be what? 1, 1. Because there is 8 plus 3. So this is 011. This is decoder what? 3. And then last decoder, which is decoder for what? 1100, which is 12, or 12, all the way to 1111, which is what? All the way to 15. So there's decoder 4. So when you think about it, it means my bits here that I have, let me use blank. I have I0, I1, I2, and then I3 respectively. So this is what I was using as my enable signals. These are what I was using. So for the first decoder, it was 00. For the second decoder, 01. Third decoder is 10. Last decoder is what? 11. And I1, I0 will be running from 0 to 1, sorry, 0011, 0011, 0011, 0011, respectively. So that was why I made this I3, I2, so that I can run them from 0001. So 0001, 10, and then 11, respectively, since I3 is my most significant bit, right? So that's how you design a 2x16 decoder using a 4x16 decoder using a 2x4 decoder, or using 2x4 decoders in that case. Yeah. So this is how you should be thinking about it in a way, right? Because here you were supposed to have just 4 inputs. So your true inputs will be this, and then this. Now you ask yourself, what about these guys? Those 4. Then you've learned about enables. You can, this is also a decoder. The decoder outputs 1 at a time. So it means only 1 will be selected at a time. Then you think about it and go with an idea of using those outputs as the enable signals. So when each of them is activated, then it will activate the respective decoder is being connected to. That's all. That's all you need here. So this is how we implement it. Any questions? Any question? It's now 7:10. So I think we can end it here. Any question? Okay. So if there are no questions, then I think we can end it here. Next time we continue with some other things. So thank you for joining today's meeting. I'll see you the next time. Bye-bye.
Speech like how we see things that everybody has this. The one that leads us the pages. So it was in some difference. The way it says,